Okay, let's recall what I did last time. Last time we know how to diagonalize a matrix in certain conditions. Okay, so the idea is, diagonal matrices, they are easier to deal with. Matrix multiplication, they are easier to deal with. Okay, so if we can relate a matrix with a diagonal matrix, then we can easily do operations on the matrix, like a matrix operations, matrix product. Okay. The idea is the following. Okay, the idea is following. So we have a diagonal matrix gamma. Then we have eigenvalues and eigenvectors for this diagonal matrix. Okay, if you do E1 to be 1 on the first component and 0 on the other component, and E2 is the second component is 1, then all other components are 0, now etc. etc. En is the vector that nth component is 1, all other components are 0. Okay, so they are orthogonal. Easily check the dot product of them, pairwise of this dot product between these vectors are 0. Okay, so they are orthogonal vectors that span Rn. So this is the standard, okay, standard basis, orthogonal basis for Rn. So they are the eigenvectors for this diagonal matrix with eigenvalue lambda I. Okay, you check, easily check. Now suppose we have a matrix A with n distinct eigenvalue lambda 1, lambda 2, lambda n. Then you check with corresponding eigenvectors v1, v2, vn, etc. etc. So now you, by definition, AV1 will be lambda 1 v1, AV2 will be lambda 2 v2. Okay, if you compare this relation with what we did for the diagonal matrix, you see, if you compare this thing, you see this matrix A, what this matrix does on its eigenvectors v1, v2, vn is exactly the same thing for the diagonal matrix. What diagonal matrix did on the vectors e1, e2, en. Okay. So somehow, if we change the basis, if we can relate v1, v2, vn with respect to e1, e2, en. Okay, so this is the idea. So we have matrix X. That's if you plug in e1, you get a v1. Plug in e2, you get a v2. Plug in en, you get a vn. Okay, so in matrix form, this X matrix is, we write in column vectors v1, v2, vn. Okay, this v1, v2, vn, they are eigenvectors for the matrix A. Then you check this matrix X exactly does change E1. You plug in E1, output V1. Plug in E2, output E2, V2. Okay, now this X is invertible because the n eigenvectors, they are linearly independent. So they span the whole space Rn. Okay, so this matrix X is invertible. So we can have an inverse, X inverse. Then X inverse, what X inverse does is you plug in Vn, output you plug in E1, output you plug in V1, output E1, plug in V2, output E2. Okay, this exactly do the opposite, the inverse for what X does. Okay. Okay, now we do this picture. You see, we plug in E1 to X, then we get a V1, and we plug in V1 to the matrix A. Then now V1 is the eigenvector of A. So we get a lambda 1 V1. Okay, lambda 1 V1. Sorry. Then lambda 1 V1, you do X inverse. So you get lambda 1 E1. Okay, so there's 3 steps. XA, X inverse, the 3 matrix, the composition. Okay, the composition operation actually looks exactly like the diagonal matrix. Okay, so you check this is a three matrix, X, A, X inverse. The composition of three operations is the same as the diagonal matrix. Okay, you check. So actually we can conclude that the three matrix X inverse A X, their composition is their product is exactly the diagonal matrix gamma. Okay, then you can use matrix operation. You can find what is this matrix A is. Okay, so A is you solve for A. Okay, you solve for A. So A is X times gamma times X inverse. Okay, so this motivates the definition of similar matrix. Okay, if we have two matrix, A and B, if they differ by invertible matrix, then so we define it. So here this is, we defined last time what the similar matrices are. Okay, remember the definition. So two matrix AB, two matrices A and B are called similar if there exists an invertible matrix P, an invertible matrix CX, an invertible matrix X, such that B is A X inverse times X. Okay, now you check this definition. Being similar matrices are actually equivalent relations. So you can check if A is similar to B, then B is similar to A. So it's reflective. Then if it's transitive, if A is similar to B, B is similar to C, then A is similar to C. So, and also it's A is similar to A. Okay, so you can check this relation is actually equivalent relation. Okay, so according to this definition, a matrix is called diagonalizable if it's similar to a diagonal matrix. Okay, definition. A is called diagonalizable if A is similar to a diagonal matrix. Okay. Okay, now if suppose A is diagonalizable, then we can do a lot. Okay, and then we have this. Okay, theorem. According to what we just did, so a matrix is diagonalizable if it has n distinct. Okay, a matrix has n distinct eigenvalues, then it's diagonalizable. So if a matrix, so n by n matrix, a square matrix A is diagonalizable. If A has n distinct eigenvalues. Okay. Now if A has less, some eigenvalues, they have greater than 1 multiplicity, okay, has higher multiplicity, then that situation will be a little complicated. So this case is easier. If A has n distinct eigenvalues, then A is automatically diagonalizable. So we'll focus on this condition. If we have a chance, then we will talk about more what happens if A has 13 eigenvalues with multiplicity greater or equal than 2. Okay. Okay. Now, first of all, powers of a matrix, power of a diagonalizable matrix. Powers of a diagonalizable matrix. As I mentioned earlier, matrix multiplication can be computationally expensive, okay, because we need to do a lot of multiplications. So if we do higher power, okay, a to the power n, so this can be really computationally expensive to use definition of matrix product. So now if A is diagonalizable, then we have, for instance, if A is diagonalizable, A is, we can write X diagonal matrix, X inverse. So here X is an invertible matrix. So here the matrix gamma is lambda 1, lambda 2, lambda n, okay, n by n matrix with diagonal entries lambda 1, lambda n, and all other entries is 0, okay. Then if you do A squared, this will be X gamma X inverse times X gamma X inverse. Okay, you see the X inverse and X. Now matrix multiplication, this is associative, okay, associative. So X inverse times X, they cancel each other, okay. X inverse times X, we get identity, so they cancel each other. Then we get, this is X gamma times gamma, gamma squared, X inverse, okay, gamma inverse. So etc, etc. So now if you do A cube, this will be A squared times A. So this will be X gamma squared X inverse times A, which is X gamma X inverse. Now again, X inverse times X is identity matrix. So they cancel out each other. So finally we get X gamma squared times gamma, so we get gamma cube. Okay, X inverse. So etc, etc. So you see A to the power n, A to the power k, see we get X gamma to the power n, gamma to the power k. X inverse. Okay, so we don't need to use definition to do matrix multiplication. So here X is invertible matrix. Now gamma to the power k is lambda 1 to the power k, lambda 2 to the power k. The diagonal thing, lambda n to the power k. Okay. Now this reduce a lot of operations. Okay. This reduce a lot of matrix multiplications if k is large. Okay. If k is large, so the computation is not so heavy. Okay. Now X is fixed here for A, if we are given A. Now what happens if k approaches infinity? Now if k approaches infinity, so the diagonal entries will either approaches infinity, it depends on lambda I. If lambda I approaches is less than 1, its norm is less than 1, then for all I from 1 to n, then you see its power, lambda I to the power k, will approach 0, okay, as k approaches infinity, So this tells us, okay, this means AK approaches, X times 0 matrix times X inverse. This we get a 0, okay, because 0 times any matrix, we get a 0. Okay, i.e., when a matrix approaches 0, when a matrix to the power k approaches 0 matrix. Now you see, if all its eigenvalues is bounded by 1. Okay, if all its eigenvalues is bounded by 1, then it approaches 0. Okay, if all eigenvalues are bounded by 1, then the power of A approaches 0. Okay, now another example, famous example, the Fibonacci numbers. Fibonacci numbers. This is famous. Okay, now Fibonacci number is defined by f1 to be 1, f2 to be 2. F2 is 1. And then for convenience, we define f0 to be 0. Okay. And then fn plus 1 is fn plus fn minus 1. Okay. For n greater equal than 2. Okay, f3 is the two terms, sum of the two terms before f3. So this is f1 plus f2. So it's 1 plus 1 is 2. Now f4 will be f3 plus f2. So this will be 1 plus 2, 3. So f5 will be 2 plus 3, 3 plus 2, 5. f8, f6 will be 5 plus 3, 8. Okay, etc., etc. Now f7 will be 8 plus 5 is 13. Okay, so we want to find a general formula for the Fibonacci number. Okay, we want to find a general formula for the Fibonacci number. Well, we can write it in this form. Okay, So use matrix form. If we write this vector fn plus 1 and fn, we can write it as this form. Use matrix multiplication 1, 1. Okay, here we have fn minus 1. Okay, root times column. Okay, root times column. So fn plus 1 will be fn plus fn minus 1. Root times column. Okay, now fn is just the root times column. Okay, 1, 0. So you check root times column, then you get fn equals fn. Okay, fn equals fn. Okay, so this is a matrix. This is matrix A. Okay, so this is matrix A. Okay, so now use this idea. You see the idea. For instance, the example. So for instance, f8, f7. This is A times f7 times f7 f6. Now f7 f6, you do this again. This is A times A f6 f5. So the n decreased by 1. The index decreased by 1. And then multiply by A. So this is A times A times A. Now the index decreased by 1 again. Okay, 5 f4, etc., etc. Okay, etc., etc. So how many do we have? How many A do we have? So this is A to the power. So you see the number, the power of A plus 7 is 8. So this is A to the power 8. So let's do A to the power 7. A to the power 7, F1, F0. Okay, so you see the only thing, F1 is 1. Okay, so F1 is 1, F0 is 0. So the only thing is to compute. The power, okay, the power of A, okay, 7 is power of A. So etc. If you have F capital F n plus 1, capital Fn, this you can get, this is A to the power n, F1, F0. Okay, F1, F0 is known. So if we have a good method to compute A to the power n, then we can determine, use matrix multiplication, then we can determine the Fibonacci number, how the Fibonacci number in general so it looks like. Now we compute we compute power of the matrix A. Okay, to find, we compute A to the power n for general A, for general n, to find the general formula for Fn, to find a formula for Fn, Fibonacci number. Okay. Now remember, to compute directly, this is computationally expensive, and we don't have a general formula. So we use the diagonalizable matrix to find the product. Okay, to find the power. Okay, to find how we diagonalize the matrix A, we do the following. Remember, we need eigenvalue and eigenvectors. Okay, so we first find eigenvalue and eigenvectors for this matrix A. So this matrix A is 1, 1, 1, 0. Okay, find its eigenvalue. So we need to compute this A minus lambda I, the determinant of this matrix. Okay, i.e. the determinant of this matrix, y minus lambda, negative lambda, 1, 1. Okay, the determinant of this matrix, 2 by 2 matrix. This is, we compute the 2 by 2 determinant. Okay, so this is the y minus lambda times negative lambda minus 1 times 1. Okay, so we get this is lambda squared, use a little algebra, so lambda squared minus lambda, and then minus 1. So to find the eigenvalues, we need to find the root. We need to find the roots of this characteristic polynomial. So let this thing to be 0. Let lambda squared minus lambda minus 1 to be 0. Then we solve by the quadratic formula. So we get a lambda 1 to be negative b. So b is the coefficient of lambda is negative 1. So it's negative b, so it's negative 1, so it's 1. So we have lambda 1 plus b squared minus 4ac, so it's you check, it's root 5. Okay, and lambda 2 is y minus square root 5 over 2. Okay, so this is actually the golden ratio. This is the famous golden ratio. Okay, golden ratio. This is the famous golden ratio. Golden ratio. This is the famous golden ratio. I think we find eigenvalue, and then we find eigenvectors. Okay, eigenvectors. So lambda 1. So it's y, y. So this is A matrix A times xy. So let's see x1, x2. Let's use xy maybe. Use xy. This is lambda 1, xy. Okay, you see the first rule says x plus y equals lambda 1x. The second rule says x is lambda y. Okay, so the vector will be, looks like this. xy will be, y is x is lambda y, so it's a lambda y y. So this is a y multiple of lambda y y. Okay, so we can choose the eigenvector. Remember, eigenvector is determined up to a scalar. Okay, up to non-zero scalar. So when we choose, we may choose a y to be 1. So choose v1, the eigenvector, to be this matrix, this vector, lambda 1 1. Okay, similarly we do it for lambda 2. Okay, similarly v2, which is a lambda 2 1. Okay, so lambda 1 lambda 2, that's the name. So you can replace 1 to get lambda 2. Replace 1, you get a v1, you get a v2 by symmetry. Okay, so now remember how we do transform the basis, the orthogonal basis, the standard basis, to the eigenvectors. So the matrix, the first, so we want X such that E1 maps it to V1, okay? E2 map it to V2. So this, the output of E1 is the first column of X, okay? So we can construct X. We can write X as V1, V2, okay? Row vectors, column vectors. So this will be V1 is lambda 1, 1, V2 is lambda 2, V2, lambda 2, 1. So this is the X. This is the X. And you can find the inverse, okay? The inverse of the 2y2 determinant. Okay, remember, by Cramer's rule, we have this is AB, ABCD. By Cramer's rule, we know it's the inverse. The inverse is, we use Cramer's rule. So this is 1 over A, the determinant, AD minus BC, times the cofactor matrix. DA, this is a negative B, negative C, okay? So if we choose this, for this general formula for the 2x2 inverse, then we can find X inverse. We know X, then we find X inverse. X inverse is AD minus BC, so this will be, apply that, okay? AD times BC, this will be lambda, AD is lambda 1 times 1, so it's lambda 1. Minus BC will be lambda 2. 1 over that. Now you plug in, okay? Plugging A here is lambda 1, D is 1, negative B, so this will be negative lambda 2 here. Negative C here, this will be, C will be 1, so this will be negative 1 here. Okay, so we find X inverse now, okay, X inverse. Okay, now we find what matrix A is. Now A, remember A will be, now the gamma, the diagonal matrix is the two eigenvalues, okay? Lambda 1, lambda 2, 0, 0, okay? 2x2 matrix. So A, according to the diagonalize, the method, the algorithm, A will be X, gamma X inverse, okay? Okay, don't confuse yourself with which X inverse with X, okay? Don't confuse with the order, okay? Okay. So AN, we already know this is X, gamma to the power N, X inverse, okay? So gamma to the power N will be lambda 1 to the power N, lambda 2 to the power N, 0, 0. Okay. Now we compute A to the power N. So this will be, so A to the power N will be X, the matrix X is, okay, the matrix X is lambda 1, 1, lambda 2, 1. This is X. Now gamma to the power N, well, that's easy. Lambda 1 to the power N, lambda 2 to the power N, 0, 0. Okay, X inverse, we already know that, which is 1 over lambda 1 minus lambda 2 times, okay, now let me copy that thing, X inverse. Okay, X inverse is here, 1 lambda 1 is diagonal. Okay, 1, lambda 1, negative lambda 2, negative 1. Okay, so this is the X inverse. So we multiply this together. Okay, multiply this together. This looks tedious, but that's not that bad. So matrix multiplication. Now the first two matrix multiply. So we get this is actually the row times column. The first y1 entry is the first row times the first column. So this will be, this matrix will be first row times first column. First row lambda 1, lambda 2 times first column. Lambda 1 to the power n and 0. So it's actually lambda 1 times lambda 1 to the power n. So lambda 1 to the power n plus 1. Now the first row times the second column. So this will be lambda 2 to the power n plus 1. Okay. And then here, the second row times the first column. It's lambda 1 to the power n. Here is lambda 2 to the power n. Okay, multiply this matrix. Y over lambda 1 minus lambda 2. Y, negative 1, lambda, negative lambda 2, lambda 1. Okay, all right. So this linear factor, we put it as linear factor 1 over lambda 1 minus lambda 2. And then the first column times the first row. First column times first row. First column times the first row. So this will be lambda 1 to the power n minus 1 times 1, okay? Minus lambda, so lambda 2 to the power n minus 1 times negative 1. Okay, so we get this the entry. And then 1, 2 entry, first row times second column. Lambda 1 to the power n minus 1 times negative lambda 2 plus lambda 2 to the power n plus 1 times lambda 1. Okay, 1, 2. Now 2, 1. The second row times first column. Lambda 1 to the power n minus lambda 2 to the power n. Okay, second row times second column. This will be lambda 1 to the power n, negative lambda 2, plus lambda 2 to the power n, lambda 1. Okay, all right. Now you see, this is a to the power n. So finally we get fn plus 1, fn. This is a to the power n, f1, f0. So this will be a to the power n, 1, 0. Okay. Now a to the power n we already know. So we plug in, substitute. This is 1 over lambda 1 minus lambda 2. This matrix, I don't want to copy it again. This matrix times 1, 0. Okay. Now multiply this 1, 0. Actually, we get the first column. Okay, the first column. The first column vector will be the first column vector of a to the power n. So this will be 1 over lambda 1 minus lambda 2. The first column will be lambda 1 to the power n plus 1 minus lambda 2 to the power n plus 1. Now here, this first column of an, lambda 1 to the power n minus lambda 2 to the power n. Okay, finally, we can compare. Okay, we can compare. So look at the second component of these two vectors. So this will be Fibonacci numbers. Okay, so look at the component wise. So the second component. So this will be 1 over lambda 1 minus lambda 2. Now the second, this is lambda 1 to the power n minus lambda 2 to the power n. Okay, so we have a general formula for the Fibonacci number Fn. Okay, here if you write this more explicitly, so remember lambda 1 is 1 plus root 5 over 2. Lambda 2 is 1 minus root 5 over 2. So lambda 1 minus lambda 2 will be actually root 5. But it's easy to check. So capital Fn will be 1 over root 5. Now lambda 1 is 1, the golden ratio to the power n, minus 1 minus root 5 over 2 to the power n. Okay, so we get a general formula for the Fibonacci number. Okay, for the Fibonacci number. Now you see, 1 minus root 5 over 2. This number has absolute value less than 1. This has absolute value less than 1. So this root 5 minus 1 over 2. This I guess around what is that number? It's 0.618, etc., etc. So its absolute value is less than 1. So that part, as n approaches infinity, approaches 0. Okay, so this part approaches 0 as n approaches infinity. as n approaches infinity. So that thing approaches so for n large, so we actually know this. This is Fn is actually is the integer near this number. Is the integer near this number. Okay, integer near this number. Okay. Now it's not necessarily greater or bigger. We don't know whether it depends on whether n is even or odd. Okay, whether n is even or odd. If n is even, so you can take either the floor function or the ceiling function, depending on whether n is even or odd. Okay, whether n is even or odd. Okay, so this is for n large. For n large. For n large. So this is the integer near this. So let's just write more explicitly. If n is even, so we subtract term that is positive. So it's less than that. Okay, less than that. Fn is less than this thing. Less than this thing. So it's a floor if n is even. If n is even. If n is odd, so Fn is this quantity plus a positive term. So in that part is ceiling. Ceiling, okay, ceiling. If n is odd, okay, if n is odd. So for instance, let's just check with our answer. Check our answer a little bit. Play around with the algebra package. Okay, play around with the algebra package. So let's see what happens if we use seed. Okay, let's see what happens if we use seed. Okay, let's see what happens if we use seed. So suppose we use A is, let's see, A is let A be square root 5. Let A be RR, I mean the RR square root 5. Okay, so now we let B to be we want 1 over A, 1 over square root of 5 times the golden ratio. Okay, 1 plus A divided by 2. Divided by 2. Okay, this quantity, this quantity. So this is the golden ratio. B is the golden ratio. So you see B is 1.618. Okay, B is the golden ratio. Or y over B is B minus 1. So this is, you should expect we get a 0.618. Okay, 0.618. So this is B or 1 over B. Either way, you call it the golden ratio. Okay, we want the golden ratio to the power. We want the golden ratio B to the power n. Okay, you see. Let's see. Now we already know. For instance, F8. What is F8? F8 is. Let's check our answer. Okay, F8. What is F8? F7 is 13. Let's see F13. F7. So we need to find B to the power 7 over A. Okay, let's find the decimal expansion of this. Okay, you see this close to 13. Okay, it's close to 13. Now, if you do B to the power, let's do B to the power 10. You see, this is close to an integer. Okay, this is close to an integer. Okay. Okay, so the Fibonacci number F10. Okay, F10 should be 55. Okay, 55. Okay, so this gives us a method to compute the general Fibonacci number quickly. I mean, we don't use inductive use the definition, recursive relation to compute the Fibonacci number. That's not effective. Okay, so this Fibonacci number, okay. Now, let's see another example. How do we actually diagonalize a matrix? Diagonalize a matrix. Now, let's see this example. Let me make this bigger. Well, let's see this example. Suppose we are given this matrix A. Okay, we are given this matrix A. Okay, 1 minute. Okay. Okay, we are given this matrix A. Let me write here. Okay. Okay, so the matrix A is given by 0, -2, -1, -2, 3, 2 here, -1, 2, 0. Okay, so this 3 by 3 matrix, what we want is we want to see if this A is diagonalizable. Okay, if it is diagonalizable, then we diagonalize it. Okay, so this matrix A, so remember to determine if it's diagonalizable, we check, we first solve its, find its determinant, we find its eigenvalues and eigenvectors. Okay, so to find its eigenvalues, we find its characteristic polynomial. So the characteristic polynomial is the determinant of A minus lambda I, this polynomial in lambda. Okay, so this is, you know, A subtract lambda I, the diagonal subtract lambda, so it's 3 minus lambda, negative lambda. And then this -2, -1. Then all other entries are fixed. Okay, this is 3 by 3 determinant. 3 by 3 determinant. So you expand by Kramer, use cofactor. Okay, use cofactors. So we expand, use the first rule, for instance, expand it using the first rule. The first rule. Okay, if we expand it use the first rule, then we got a negative the first one entry and then the cofactor. And then for the second one, we then we got a minus times -2, and then we delete the rule, the rule and the column that has this 1, 2 entry -2. So if we delete, okay, let me color this in some color. Okay, let's use the red. So to do the second thing, we just delete the first rule and the second column. Then what is remaining is -2, negative lambda, 2, -1. Okay. Now for the third entry -1, then let's use blue or use green. Let's use green. Okay, green. So we delete the third column and the first row. So it's plus -1 times what the remaining is -2, 2. 3 minus lambda, here is -1. Okay. Now 2 by 2 determinant, we already know how to expand 2 by 2 determinant by definition. Okay, A, B, C, D, a matrix, then we just use AD minus BC. 2 by 2 is easier. Okay, so this we get, this is negative lambda, 3 minus lambda times negative lambda minus 2 times 2, 4. We plus 2 here, then multiply -2 times negative lambda, so we get a 2 lambda minus negative 2, so it's plus 2. And then minus, so we get a negative 4 minus 3 times lambda. Okay, 2 by 2 determinant are easier. So finally, expand this. Expand this. Now it's better to use seed. It's better to use seed. Okay, it's better to use seed. Now here, now expand this, and then factor it. So somehow I'm cheating. Use elder package. So you get actually this negative lambda 1 lambda plus 1 squared lambda minus 5. Okay, let's see, do the dirty algebra work. Okay, so we find the characteristic polynomial. Characteristic polynomial is this. So you see the factor lambda plus 1 has a multiplicity 2. So this means we do have a multiplicity. So in this case, we let the characteristic polynomial, we set the characteristic polynomial to be 0, and then solve for its roots. Then its roots are the eigenvalues of the matrix A. Okay, so we have lambda 1 equal to lambda 2 equals negative 1. So we have multiplicity 2 for the eigenvalue lambda negative 1. Okay, another lambda 3 is 5. So this is the 3 eigenvalues of the matrix A. So lambda 1, lambda 2, they are the same. We have multiplicity 2. Then we find eigenvalue. We find eigenvalue, and then we find eigenvector. Okay, how do we find eigenvector? Okay, so we use the matrix A minus lambda I. So let's do lambda 1, lambda 2. Let's see how do we find eigenvalue. We already know eigenvalue. Now how do we find eigenvector? Okay, eigenvector, remember eigenvector is the vector in the null space of A minus lambda I. Okay, A minus lambda I, or A minus lambda 2 I. So this will be A lambda 1 is negative 1, so it's a plus I. Okay, A plus I. So this will be, we want to find the null space. We want to find the null space of this matrix A plus I. So this A plus I, we already have A. So let's just add 1 to the diagonal. So let me, you can believe me here now. So it's negative 1, negative 2, negative 1, 2. Now the diagonal, we add 1. Okay, and then here this is 2. So this is the, you can check, this is actually the matrix A plus 1 at the diagonal. Okay, remember we have this matrix, where do we have matrix A? This is the matrix A. Okay, this is the matrix A. Then we add 1 to the diagonal. Okay, all 3 diagonal inches. Then we get A plus I. Okay, so this is the A plus I. Okay, now we want to find the null space, a vector in the null space. While we do, remember null space is invariant. Root space, the null space does not change if we do elementary rule operations. I.e., we can multiply a rule by a scalar, non-zero scalar. We can swap the 2 rules. We can add a rule by a multiple of another rule. Okay, we do rule operations to make it an upper, to find its null space. Okay, so while you see, first of all, this is rule 1, rule 2, rule 3. Okay, now if we add a rule 1 to rule 3, you see this is, we add a rule 1 to rule 1, add rule 1 to rule 3. You see, rule 3 will be negative 1 plus 1, 0, 2 plus negative 2, 0, 1 plus negative 1, 0. Okay, R2. So R2 adds twice R1, replace to R2. Now negative 2 plus 2, this 0, 4 minus 4, 0, 2 minus 2, 0. Then rule 1 is 1, -2, -1. So the root space is spanned by, the root space is spanned by this, so root space is one-dimensional, is spanned by the vector 1, -2, 1, -1. So the new space is orthogonal to this root space. So we should have two-dimensional new space. So we find like two bases of this new space. For instance, there are a lot. You can easily find a lot. Okay, easily a lot. The vectors that are orthogonal to this, this spanned by root 1. So for instance, it's very easy. You just solve this equation. Solve, for instance, suppose the vector x, y, z is orthogonal to the root space. Okay, we want the dot product 1, -2, -1. This is x minus 2y minus z is 0. So there are a lot of choice. You can just, for instance, you can choose option x and you can choose option yz as free variable, and then you solve for x. So for instance, if you let z be 1, you get actually y to be 0. Okay. Now if you let y be 0, y be 0, sorry, y to be 1, z to be 0. Okay. You see this, you view y as yz as free variable, you solve for x. Then you got x is 2. Okay. So we have two variables, two v1, v2. Okay, v1, v2. v1, v2. Now you see in this case, when we have a multiplicity, we can, there are still two distinct eigenvectors. Okay, now we normalize it, use Gram-Schmidt. Use Gram-Schmidt. Actually, we only apply just subtract v2 by the projection on v1. That's pretty easy. So we just fix v1. Fix v1. So u1 is 1, 0, 1. U2 is we subtract v2, subtract the projection of v2 on v1. So what is the projection? V2 on v1. So it's the v2, the projection on v1. So this is the v1, v2 dot product v1. Okay, over v1 of v1 norm. Okay. I think v1 dot v2. So v1 of v2 dot v1. You get a 2 plus 0 plus 0. So it's actually 2. Norm of v1. Norm of v1 is square root 1 squared plus 1 squared, which is square root 2. Okay. So this will be v2 is 2, 1, 0. Subtract twice over root 2. Times didn't get some mistake. v1 is 1, 0, 1. Okay. Yeah, why do we have this choice? This is not what I want. Okay. Yeah, we want orthogonal. We want them to be orthogonal. Yeah, actually, this we just subtract. Okay. Okay, it should be normal squared here. Normal squared. It should be somewhere. It's normal squared. Where did I get something wrong? Okay, it should be here. U2 is this one actually will be orthogonal. V2 subject V1. V2 subject V1. Then this will be okay, the dot product is okay, so did I get something wrong? Yeah, I forgot what copy. Yeah, I forgot. Sorry. The projection of V2 on V1 it should be this thing, V1 thing. This is the unit vector, but we should we do dot product. To get the projection, we need also divide by the norm of V1. Okay, this will work. This V1 dot V2 will be 2. This 2 over root 2 times 1 over root 2. Okay, so this is actually exactly V2 subject V1. Okay, V2 subject V1. Okay, so V2 subject V1 will be, so this 2 1 0 minus V1 1 0 1. So we got this is 1 1 negative 1. Okay, you check. It's very easy to check. U1 is 1 0 1 and this U2. Now they are orthogonal. 1 1 negative 1. You just do the dot product, you find actually they are orthogonal. And then we do normalization. So we get the unit vector. Okay, 1 0 1. P2 is 1 over root 3. 1 1 negative 1. Okay, all right. So now we need to actually find lambda. Do it for lambda 3. Lambda 3 is 5. So we find an eigenvector. So we need to find this null space A plus 5i. Sorry, A minus 5i. A minus 5i. So this will be this negative 5, negative 2, negative 1. Okay, negative 2, 3 minus 5. So this will be negative 2, 2. And then this will be negative 1, 2, negative 5. Okay, so this should have rank 2. This matrix should have rank 2. So we do rule operations. Okay. Do rule operations. So if we switch the rule, so we get negative 1, 2, negative 5, negative 2, negative 2, 2, negative 5, negative 2, negative 1. Switch the 3 rules. Rule 1, rule 2, rule 3. Now we cancel entries. So what do we do is let's see what do we do to rule 2. Let's rule 2 add negative 2 multiple of rule 1. Replace it rule 2. And rule 3, what do we do is rule 3 add negative 5 multiple of rule 1. Replace rule 3. Okay, so this will be rule 1 keep it fixed. Negative 1, 2, negative 5. This will be negative minus 2 multiple. So this got a 0. Negative 2 minus 4. So we get a negative 6. 2 minus 10. Sorry, 2 plus 10. 2 plus 10. 2 plus 10 is 12. This should be 0. Negative 2 minus 10, so it's negative 12. Okay, now negative 1 plus 25. Negative 1 plus 25 is 24. 24. Then this is root 1, root 2, root 3. Now you do root operation again. You do root operation again. So you see that root 3 add negative multiple of root 2. Replace root 3. And then root 2 we divide by negative 6. So this will be negative 1, 2, negative 5. 0, 1, negative 2, 0, 0. Okay, 0. Okay, so you see here we can choose it to be the new space. The new space, okay, to the new space. Okay, so we check the new space should be negative x plus 2y minus 5z is 0. And then y minus 2z is 0. Okay, so z is free variable. Z is a free variable. Z is free variable. Okay, so we get y is 2z, and x is 2y minus 5z. So this is 2y is 4y, y is 2z, so it's 2 times 2z minus 5z. So x is negative z. Okay, so the equation, the new space is x is negative z, y is 2z, z is a z. So it's you get a z multiple of negative 1, 2, and 1. Okay, so we can choose this as eigenvector. So at V3 choose V3 to be negative 1, 2, 1. Okay, now we need to normalize it. We choose it to be P3. Normalize it by its norm. So V3 norm is square root negative 1 squared plus 2 squared plus 1 squared. So it's root 6. So normalize it. So then we get P3, the unit eigenvector. So it will be negative 1 over root 6, 2 over root 6, and 1 over root 6. Okay, so finally we can diagonalize A. Okay, so we find 3 eigenvalues orthogonal. Okay, we find 3 orthogonal eigenvalues with unit. Okay, with unit vector. So those 3 vectors, 3 eigenvalues is negative 1, negative 1, and 5. Okay, so this is okay. Now remember the X matrix. The X matrix should be what? X is we write X as 3 columns. Okay, 3 columns. 3 columns of 3 columns. Okay, X is 3 columns of this thing. So X is, so remember A is the diagonal times X inverse times X. Okay, so A will be, the X is this matrix. Okay, X is, we write column vectors of the 3 eigenvalues. Okay, 3 eigenvalues, 3 eigenvectors. Then we have the 3 eigenvectors, which will be 1 over root 3, 1 over root 2, 0, 1 over root 2. So this is a P1. Now P2 is 1 over root 3, 1 over root 3, negative 1 over root 3. Now P3 is negative 1 over root 6, 2 over root 6, and 1 over root 6. Okay. Okay, so here if you write this as unit vector, then x inverse is the x transpose. X inverse equals x transpose equals x transpose. If you write this, they are also normal vectors, also normal vectors, also normal column vectors. Then x inverse is x transpose. Okay, you will see why. Okay, x inverse is x transpose because let me explain in this in a moment why x inverse is x transpose. So here x inverse is x transpose. So we don't need use Cramer's rule to compute the inverse again. So here x inverse is x transpose. So x transpose, you write row vectors as column vectors. And then this is negative 1 over 6, 2 over 6, 1 over 6. Now we can diagonalize this matrix A. Okay, we finally diagonalize this matrix A. Now remember, be careful. Diagonalize a matrix is the form that we diagonalize it is not unique. Okay, it's not unique. Okay, it can you can get different kind of a diagonalize different form. For instance, if you choose different bases, you actually get looks like different. Okay, look like different. Okay. So the diagonalization it can be different, looks different. Okay, now let me explain why x inverse is x transpose. Why? Okay, now you see if we write x as, it's 3 eigenvectors p1, p2, p3. 3 eigenvectors. So they are also normal. Okay, they are also normal. Okay, also normal. So which means pi times pj is third ij. Third ij is 1 if I equal to j. If I equal to j, I equal to j. And 0 otherwise if I differs from j. So this is a canonical third. Okay, the famous canonical third. So x transpose, you see what x transpose? If x we write as column vectors, x transpose will be the column vector will become a row vector. P1, P2, P3 in row vector form. Okay, in row form. Okay, now you see x times x transpose. Okay, the ij. Okay, the ij entry. The ij entry will be what thing? What do we get? Let's use x transpose times x because that's easier. Okay, so this will be x transpose. So this will be p, p2, p3. Okay, now p1, p2, p3. Now you see the ij entry is the ith row times j column. So you see the ij, this ij entry is exactly pi times pg, dot product with pg. Okay, dot product with pg, pi times pg, which is a third ij. If I equal to g, this is 1. If I is different than g, this is 0. So actually we see this thing is so when I equal to j, we get a diagonal entry with 1, then all other entries are 0. So this is actually nothing else, is the identity matrix. Okay, so this tells us that x transpose is actually x inverse. So if we know the column vectors are also normal vectors, then we know X transpose equals X. Okay, so theorem. If X is a square matrix with also normal column vectors, then we know X transpose equals X inverse, or X inverse equals X transpose, because X inverse, if you want to compute X inverse by Cramer's rule, that will be a disaster, because Cramer's rule has a lot of computations. Okay, now we know how to actually diagonalize a matrix, if it's possible. Okay, in certain case, diagonalization is not possible. Okay, at least we know a matrix is diagonalizable if it has n distinct eigenvalues. Okay, if we have certain multiplicity, okay, some eigenvalues are the same, it's possible that this matrix A is not diagonalizable. But sometimes it can be like this example that we talked about. This example is diagonalizable. Okay, to answer this question, when a matrix is actually diagonalizable, this actually beyond the scope of this course. Okay, so we will not talk about that question. Okay, so but we know for certain large class of for matrices is diagonalizable, at least when the matrix has distinct eigenvalues. Okay. Okay, homework problem for this section. Homework for section 6.2. Let's do number 1, number 2, number 6, number 19, number 29, and number 30. Okay. Okay, all right. Now let's talk about the next section. System of differential equations. Okay. System of differential equations. Differential equations. Okay. Now the idea is, in physics, we have a lot differential equations. We want to know how certain quantity changes with respect to time. Okay. Now we need to, how a quantity changes. This is, derivative. So in physics or in some reality, we want to know how certain quantity changes. Some quantity changes with respect to, for instance, time. Now this, we should study the derivative of certain quantity. So for instance, example, position function of certain object, position function, R equals RT. Okay. Now, for instance, velocity, how velocity changes, velocity VT. And we know velocity, the change rate of position function, RT, is given by velocity. Okay. Now, acceleration. At is derivative of Vt. Okay, let me use Leibniz notation, dt, Vt. Okay. Now these things, they are vectors. Okay, velocity, position, they are vectors. They are vectors. Now Newton's second law. So Newton's second law is fundamental in mechanics, Newton mechanics. So it unifies, how the Earth travels along the sun, how the moon travels along the Earth. So Newton's law actually unify all these things with the mechanics of objects on the Earth. Okay. F equals ma. Okay. Now here, this is, if you write this thing as m d squared, second derivative of this vector rt. So this is one example. So we have this second differential equation in physics. So Newton's law actually, people then find in certain situations that Newton's second law is not valid. Newton's second law is not valid. Like quantum theory, in quantum theory, Newton's law describes a lot of things. Okay, Newton's law describe a lot of things. Then in the beginning of the 20th century, that people find in some situations that Newton's law does not apply. So that's part of the thing motivates Einstein's theory, relativity, and part of the thing motivates quantum physics. And we have a similar equation that describes describe a system, okay, that comparable with Newton's law in Newton mechanics. That's a Schrodinger's equation. That's famous Schrodinger equation. So Schrodinger equation. Schrodinger's equation. That's the most famous equation in quantum mechanics. Okay, Schrodinger equation. I imaginary number. Each bar is a constant. Planck constant. Okay, this is the vector as we explained earlier. So this H is called this H is a matrix that is described by that describes the energy of the system. So you have actually a matrix, okay, matrix equation, differential equation in matrix form, okay. So this is why quantum mechanics is also called matrix mechanics, okay. It describes how the systems of a quantum system, how the state of a quantum system changes, okay. The reason that causes the change of this quantum system is actually determined by a matrix called Hamiltonian. Okay, so the H is a matrix that actually explains the reason how the system changed. So this matrix H totally determines how this quantum system changes. Okay, actually it's a matrix equation. It's matrix equation. Then we in this section we talk about this matrix differential equations. So it looks like this: how a vector u changes du over dt is actually a matrix A times this vector u. Okay. Here u is a vector in maybe let's see for instance in Rn. Here A is a matrix, n by n matrix with real coefficients. Let's see. Okay, so the matrix A tells us how this u changes, how the vector u changes with respect to time. So the matrix A can choose how the system, how the vector u changes with respect to time. Okay, how the matrix A can choose the evolution, which is the word evolution. Okay, how certain thing changes with respect to time. The matrix A can choose the evolution of the vector u. Now, if we know the initial state, i.e., if we know how the vector u, the initial position, initial state of this vector u looks like, then we should totally determine the evolution of this vector u with respect to time. Okay. If we know the initial state of this vector u, now we know how this u, the evolution of this u. Okay, so this totally determined. Okay, the matrix A, how this matrix A looks like, it actually has two cases. Okay, these two cases are very different. The first case, two cases. The first case is when A is independent of time. A is constant. A is a constant. A matrix that doesn't depend on time. Okay, A is time independent. Okay, time independent. So it's constant with respect to time. Constant matrix. Time independent. Now the second case, in the first case is easier. The second case, A is time dependent. So A is time dependent. So A is 80. In this case, this is far from solved. Okay, this case, the second case is very difficult. It's far from solved. So the second case is beyond the scope of this course. Okay, it's beyond the course. This course. The idea to solve the second case, we just choose a small time interval. Okay, choose a small time interval and view this A is constant. Okay, view this matrix does not change too much. So view A is constant and use equation 1. Okay, use type 1 to solve. Okay, and then glue them small pieces together. Glue these small pieces together. Okay, so just if you have a time interval, you break it into many small time interval and view that each small time interval does not change too much the matrix A. And then multiply all the cases together. It can be super complicated. Okay, for time dependent case. Okay, so case 2 is beyond the scope of this course. So we only talk about case 1. Okay, case 1. We only talk about case 1. Case 1. A is time independent. Okay, now if we look at the lower degree case, when the matrix is just 1 by 1 matrix, just a number. Okay, so trivial case, for instance, we have dy over dy over dt. This is lambda of y. Okay, lambda times y. So y, the matrix is 1 by 1 is number. The vector is 1 by 1 is just a number. So here we get dy over dt is lambda y. Now we just talk about how do we solve a differential equation. So we write it in this form. Remember, dy dt, the Leibniz notation, we can manipulate the differential. So we get dy is lambda y dt. If you divide by y, so we get a 1 over y dy. This is lambda dt. And then if you integrate, you integrate y over y dy. This is lambda dt. Lambda is constant, so this is lambda t plus constant c, plus constant c. Okay, plus constant c. Now this side you get this line absolute value of y. Okay, so you get actually so you get this thing equals that. So you take the absolute value of and then apply e. So you actually have y equals y0 times e lambda t. Okay, when you take consideration of this constant c, you plug in t0. So the y0 is such that if t equal to 0, so y equal to y0. E to the 0 is 1. Okay, so the solution is this. Okay, solution is this. Okay. Okay, now this motivates how we solve the matrix equation. Remember the exponential function ex, we can define it to be by a Taylor polynomial. Okay, Taylor polynomial. Taylor expansion or Maclaurin. It should be Maclaurin. Okay, so it's x to the power n over n factorial, sum over n from 0 to infinity. And by definition, 0 factorial is 1 by definition. Okay, now we actually define the matrix form. So we define the matrix form. So if we get du over dt is AU. So the equation is actually this. The solution is U equal to UT. U is a vector, remember? UT is U0 vector times, let's see this. This should be this, e to the AT U0. Where the matrix exponential is defined as this. Okay, e to the matrix AT is defined as this. When t is 0, so this is identity plus, so view, let me do it, let's do e to the a is defined as this. E to the a, replace x by a. Okay, so this is a squared over 2 factorial plus a cube over n factorial plus etc. etc. Okay, now this is well defined. This is well defined. Okay, this is well defined. This is well defined. Why? Because for any fixed matrix A, now the you use matrix multiplication. You actually you can show that the growth rate is controlled by factorial. Okay, so it does not increase too fast. And then the n factorial dominate the matrix multiplication. So actually this converges. There's no problem. So this is well defined. There's no divergence issue at all. It's defined for all possible matrix A. It's defined for all square matrix. So it's well defined due to its quick convergence. Okay, so there's no issue about the divergence issue at all. It's defined everywhere. Now you see e to the AT, similar to e to the AT will be I plus AT plus a squared t squared over 2 factorial plus a cube t cube 3 factorial, etc. etc. So you can actually check its derivative with respect to t. Now identity does not is 0. So identity matrix derivative 0. AT derivative is a. Now a squared. So this get this we got AT squared. This we got sorry. This we got a squared t. Sorry. This we get a cube t squared over 2 factorial, blah, 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 blah. If you factor out a, so this will be a identity plus at plus a squared t squared over 2 factorial, etc., etc. So this will be a e to the at, okay? Okay, so the solution in this case, du dt is au, okay? This solution has this solution. Solution is this solution. A is time independent. So the solution is ut is e to the at u0, okay, times u0. Okay, be careful, be careful. We should write the matrix e to the at on the left, okay? We can, you know, in general, matrix multiplication is not commutative. It's not commutative. So this is the key difference with the dimension 1 case. Okay, then you check. So we also have a product rule, of course. Du over dt is d dt. So you use product rule, okay? Now you know, u0 is derivative 0, so this is actually e at dt u0. Then this is a times e to the at u0. Okay, now this is e to the at u0 is actually ut. So you see ut actually satisfies this equation. Ut satisfies this equation. Okay. Okay. Now, why do we know this is the unique solution if we know u0? Okay, because the evolution is totally determined. If we have one solution, then that's the unique solution because the evolution is totally determined. So there's no other choice. Okay. Okay. Now, if A is diagonalizable, that will be looks a lot nicer. Okay. If A is diagonalizable, i.e. A equal to x gamma x inverse. X is invertible for some x invertible matrix. Then you see gamma is this matrix, gamma lambda 1, lambda 2, lambda n. Okay, then you see a to the power k, as we know, this diagonalizable matrix, its power can be easily computed. Its power can be easily computed. This is x gamma to the power k, x inverse. So this will be, okay, now this will be x lambda 1 to the power k, lambda n to the power k times x inverse. So e to the at, this will be, now if you write this as I plus at, use definition, plus at squared or 2 factor Now if you use definition, this will be I plus x gamma x inverse plus x gamma squared x inverse t squared over 2 factorial Now if you factor out, so if you write in this form, if you write I as x times x inverse, so you actually get x times x inverse here. This you get I plus gamma t plus gamma squared t squared 2 factorial plus etc. etc. Okay, this will be x. Now remember, this will be I plus gamma t. Remember what gamma t looks like? Lambda t, lambda nt Now gamma squared t, this will be lambda y squared t squared over 2 factorial. Da da da. This will be lambda n to the power 2 squared 2 factorial. Plus da 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 x inverse. Okay, so I is the diagonal entry is just 1. So this will be x. Now the sum of this thing, the matrices in the bracket, in the parentheses will be, so its diagonal thing will be, the thing will be y plus lambda 1t plus lambda 1t lambda squared t squared 2 factorial plus da 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 da. So here the second entry will 2 entry will be y plus lambda 2t plus lambda 2 squared t squared over 2 factorial da 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 plus so here the last entry will be lambda n y plus lambda n t plus lambda n t squared over 2 factorial da 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 x inverse. So this actually you got this thing. X, this E gamma t, x inverse. Okay, E gamma t is this matrix. E gamma t is this thing according to what we just write explicitly. This e to the lambda y, e to the lambda 2, da 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 da, e to the lambda n. Okay. Okay. Okay, so if A is diagonalizable, then that will be really easy, really easy. Okay. If gamma is a diagonal matrix, then e to the gamma t is also diagonal matrix. Okay, so if so this E is diagonal matrix. Diagonal matrix. Okay. Now if we let's see what happens if we have eigenvalues and eigenvectors. If we have this thing, if we know AV equal to lambda V, i.e. V is eigenvector of A with lambda eigenvalue. So what do we know about e to the A, e to the AT, e to the ATV? What do we get? Okay, now this actually we will get e to the lambda t V. Okay, you can check. Okay, if you expand e to the AT times V, so this will be identity plus AT plus A squared T squared 2 factorial blah 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 times V. Now this will be I times V, so this will be YV. Okay, so this will be Y plus AV is lambda. Okay, so you got a lambda TV. Now we factor out of V. Now A squared V, you get a lambda squared T squared 2 factorial. Da 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 da. This is the V. This is exactly e to the lambda t V. Okay. Okay. Now what happens for this e to the AT? Now this e to the AT is also called evolution operator or evolution matrix. Evolution operator or matrix. Okay. Okay. Now you see if we know the eigenvectors form a basis. Now for any u, if we know if the eigenvectors form a basis, then for any u, we can write as, for any u in Rn, let's see, we can write it as u to be let's see, C1 V1 plus etc. plus Cn Vn for unique C1 for some numbers. Okay, totally determined numbers C1, C2, Cn. Then you see what do we know? E to the U0. Okay, e to the at U0. This will be e to the at, use linear property, C1 V1 plus Cn Vn. Okay, this we get use linear property distribute. So this we get C1, you see e to the at on V1 plus e. Okay, plus etc. plus Cn e to the at on Vn. Now this you can write as C1 e to the lambda 1t V1 plus etc. plus Cn e to the lambda n t Vn. Okay, let's see how this example works. Okay, let's see how this example works. Let me maybe give you one example. I think we call it a day. Okay, let's see at least one example. Let's see this example. du over dt du over dt is this, is AU, is this matrix 0 1 1 0 u. Okay, here u is xy. U is xy. Okay, xy. Now if you write this as okay, u is xy. Okay. Okay, maybe the file is too big. Let me change it to another file. Okay. Okay, let's see this example. Du over dt is 1 1 0 0. Here u is xy. Okay, if you write this explicitly, let's see u0 is 4 2. Now the eigenvector, this matrix A is 0 1 1 0. So the eigenvector of A is this. Eigenvector we just v1 is 1 1. V2 is 1 negative 1. So see the initial value. The initial value is u0 is, you see what we get is this or easy 3v1 plus v2. You can easily check. So ut will be e to the at, u0. So this will be 3 now 3 e to the lambda 1 t v1 plus 1 e to the lambda 2 t v2. So this will be lambda 1 is 1. So it's 3 e to the t times v1 1 plus e to the negative t 1 negative 1. Okay, so we can actually get this is a 3 e to the t plus 3 e to the negative t, 3 e to the t minus e to the negative t. So we get a x is this. So we get x equals xt is 3 e to the t plus e to the negative t. And y equals yt is 3 e to the t minus e to the negative t. Then we're done for this example. Next time we will explain more and see how we solve it in using the differential equation technique to get the same answer. Okay. Next time we will talk more about this technique. How do we solve differential equations using matrix? Okay. Maybe it's good time to stop here for today, and I will see you tomorrow.